Hello everybody. I got a question today about the difference between classical and empirical probability. And so I'll discuss that and I'll give some examples. All right, because I think we can discuss it all day long, but it's probably the case for most people that you need to see some examples, maybe several examples, to understand these individually and to see the difference. Now, in classical probability, we find the probability of event E as the total number of ways that that event can happen over the total number of possibilities. But there is no observation or experiment in determining this. So if I'm going to figure out how many ways can this event E happen, I do that totally in my head. It doesn't rely on anything that actually happens, okay? And I'll give you an example of that in a minute. All right, but it's like no observation, no experiments, just thought. So think of classical probability as just thought, okay? Empirical probability, on the other hand, I guess these formulas aren't really different. They're just phrased a little bit different. But we calculate the probability of event E as the frequency of that event E as it was observed. How often did the event happen? That's what I mean by the frequency of the event divided by the total frequency. Again, with like the frequency of like everything that happened. But both of those are totally 100% determined by observation or experiment, okay? So like if it came down to flipping a coin, we could flip a coin and like record all the results. We could take a survey of voters or something. It's going to come down to more than thought. It's going to come down to observation, experiment, something like that you can really do with the world somehow, okay? Now, all right, that's in concept what they are. Let's look at the examples, okay? So I took this one from my math lab, and it says we have a probability experiment consisting of rolling a six-sided die. We probably know what that is, but it's something you roll and a number randomly comes up, 1 through 6, okay? Find the probability of the event below, which is rolling a number less than 3. Okay, now I'm going to do this totally in my head. I don't have a die here to start rolling. And that's not the intention of this question. The intention of this question is not to get a die, start rolling it, and figure out how often you get a number less than 3. Okay? We're not going to roll a die. We're not going to do any of that. This is classical probability. We're going to determine this without ever rolling a die. Okay? So just in concept, to like just think about it. What does this mean? Rolling a number less than 3, that would translate to rolling a 1 or a 2. Now, can you tell me without rolling a die how many ways that can happen? It can happen 2 ways. I mean, you can roll a number less than 3 2 ways, right? So with our definition up here, it's like, well, how many ways can the event happen? That's what goes on top. All right. So there's 2 ways to roll a number less than 3. How many total possibilities are there when you roll a die with 6 numbers on it? There are 6 possibilities. So now, I did, like I'm emphasizing here, I never rolled a die to figure this out. That's what classical probability amounts to. There are some examples with decks of cards or flipping coins or so on. And if we're going to approach those with classical probability, we don't look through the deck of cards. We don't flip the coin. We don't roll the die. Okay? We figure these out completely by concept. All right, so that's what classical probability is. Let's see in contrast with some empirical probability. So that would be like this one. So look at this example. A company conducted a survey to determine how prepared people are for a long-term power outage, natural disaster, or terrorist attack. So, you know, this is observational. These numbers weren't come up with in somebody's head, right? Like here, there are 2 ways to roll a number less than 3. I don't need to roll a die to figure that out. Classical probability. Here, though, I mean, how would you know if somebody was very prepared to handle a long-term power outage without doing a survey and asking? I mean, how could you possibly know that? I mean, maybe you could make a guess, but, you know, without an observation, a survey of some kind, then you just have no idea. Okay. So we got this data from this observation, this study, and it rates people's responses. There, out of all the people that responded, there 264 felt very prepared for a long-term power outage, etc. And then 73, they have no clue, right? Okay, but that's the information that we have. That's empirical, all right? Now, so the question is, what's the probability that the next person surveyed, so this is the survey up to this point, what's the probability that the next person surveyed is very prepared? Well, we'd have to base that on what we've seen so far. So we'll say the probability that the next person surveyed is very prepared will be, how's it worked out so far? So far, 264 people were observed to be very prepared, but how many total outcomes or events have there been? That would be all of this, right? I mean, there were 264 very prepared out of 264 plus 969 plus 536. That's the total number of observations, okay? So that's how we would calculate an empirical probability based on data and observations. Okay, well that works out to be about 0.122 in my math lab says to round to 3 decimal places. So you see the difference there. One, we don't need to roll the die. We don't need to make observations. The other one is 100% based on observations, okay? All right, there's just no way we could come up with this information without asking people, without observation, without doing a study. All right, let's look at one more. And so in this one, it says that we're given the data in kind of a weird way, but they're observations, okay? These aren't numbers somebody just thought of, like with my rolling a dice example, right? I just thought, like, I know in my head without rolling a die, there are 2 ways to roll a number less than 3, okay? But like, how would you get these numbers without doing observations or study? What it says is there are registered voters in an election, and a little more than 3 million voted in the election. That's this number, 3,142,863. And then on the other hand, about 3,354,941 of the registered voters didn't vote. So you've got registered voters, this many voted, this many didn't. Okay, so those are the observations, that's the data. That means that this would come down to a calculation by empirical probability. Question is, what's the probability that a registered voter voted in the election? So I'd have to put something together like, well, how many registered voters were observed to vote versus on the bottom the total frequency of all the possibilities that could have happened, okay? So I'd say, all right, you want the probability that a registered voter actually voted? Well, it was observed that 3,142,863 registered voters voted. That's the number that goes on top. But then the total frequency, all right, that would be, well, I mean, of all the possibilities, the registered voter either voted or didn't. And so I add those numbers together to get the total frequency, all right? So that's 3,142,863 plus this other number, the number that didn't vote, 3,354,941. So this many voted out of this many total. It's kind of like that. That's how probability formulas work. Again, in my math lab, it said to round to 3 decimal places, and that turns out to be 0.484. Okay, so I hope that that highlights the difference between these two formulas. The formulas themselves may look and sound different. They're not, though. They're both fractions. They're both divide. You have a total on top, a total on bottom. It's just that in classical probability, we get these numbers from our heads without observation or experiment. In empirical probability, you will be given data, the result of observation, surveys, whatever, something like that. And then you use those numbers. But that's the difference. That's the only difference between them.